Hello everyone, my name is Dawson Smith, and for the past summer and semester I've been working on observing fracture and mechanics of cellulose nanocrystal thin films under advisement from Dr. Chelsea Davis and graduate student Hayam Sun of the School of Materials Engineering. So what are cellulose nanocrystals? Well, they're rod-shaped nanoparticles that can be chemically extracted from cellulose, namely trees, but also includes plants and bacteria. What we can do is we can take a chunk of wood, delignify it, remove the lignin, which leaves us with this single cellulose chain unit. Then we can treat it with sulfuric acid, and that'll make all of these chains want to stick together into a big rigid crystal. And here's an example of these in the scanning electron microscope. You can see that they're very long and not very wide. And what are some applications of this? Well, cellulose nanocrystal thin films are transparent and flexible often. So some cool things that some people have done are create bendable solar panels, transparent films. And then lastly, cellulose is 100% biodegradable. So it's of great interest to replace polymeric materials in food packaging. What I've been working on is cellulose nanocrystal thin film fracture. So there are two terms that I want to get you guys caught up on real quick. First is modulus, which is a material's resistance to deformation. This means the higher the modulus, the harder it is to pull on. Second is fracture strength, which is the force per unit area when a material breaks. And there are also some bonds that I want to get you guys caught up on too. Cellulose nanocrystals, each individual chain, are connected by weak hydrogen bonds. You can see them outlined by these red arrows here. Whereas along the length of the chains, we have stronger covalent bonds. This means that the properties of the cellulose nanocrystal are going to vary based on which direction we're pulling on them from. So once these crystals all align, it's going to be harder to pull on them axially than it is transversely. We can make a thin film out of these crystals. Take one of these individual units, we'll have hydrogen bonds and van der Waals forces connecting each of these bricks together. So the film is going to fracture in between crystals because it's weaker there. There are two other terms that I want to get you guys caught up on. One is order and the second is alignment. Order is basically a measure of how many cellulose nanocrystals are facing the same direction in the film, whereas alignment is the angle mismatch between the direction that the cellulose nanocrystal is facing and the direction we're pulling on it. So, as we can imagine, if we're pulling on the axis of the cellulose nanocrystals, the film is going to be stronger. If we're pulling against the axis of the film is going to be weaker. And this basically only emerges at higher orders. So it's pretty linear at no order when all the alignment is random, we see no difference. But as we increase the order, how many are facing the same direction, then we see a big difference in the mechanical properties. And there's been some simulation work done by close friends of our group, Dr. Mehdi Shishabor and Dr. Jeffrey Youngblood, and they simulated cellulose nanocrystal fracture. We see the same thing. Pulling on the films axially, they're stronger, and as we increase that alignment between cellulose nanocrystal and tensile direction, we see the films get weaker. The simulations predicted three fracture modes. One, a sliding mode in which cellulose nanocrystals pull past one another until the film breaks. One, a normal mode in which the interface between crystals fractures. And then a mixed mode in which you can see evidence of both, the normal mode here and the sliding mode here. So our goal for this project is to identify the modulus, the fracture stress, and the fracture mode of cellulose nanocrystal films as a function of their alignment by observing tensile tests. Some previous work has been done on this experimentally. The researchers made a sandwich composite of PDMS, which is a soft substrate, cellulose nanocrystals, which are pretty rigid, and then more PDMS. What they did is they cut out three different angles of this composite, 0 degrees, 45 degrees, and 90 degrees, and put them in a tensile tester above a microscope so that they could see fracture. We've got some cool results. As we expected, the films are stronger along that axial direction and weaker along the transverse direction as we increase the alignment angle. However, the values predicted for the modulus and the fracture stress from the simulations did not agree with experimental evidence, so we'll get to that in a moment. Here's some videos. You see the sliding mode, first of all. You see the normal mode, during which cracks propagate completely vertically and very linear. And then we see the mixed mode, and these cracks propagate at an angle with respect to the tensile direction. So as I mentioned before, the simulated values for the modulus and the fracture strength were far from expectations, and so it is our goal to improve the experimental setup and to hopefully gain more accurate conclusions. And here's what I've been working on for the past summer and semester. So basically we have a 5-layer setup, and I'll walk you through each one of these. The first is a glass slide that keeps everything flat. Next off, we deposit polyacrylic acid. It's soluble in water, and that makes it so we don't have to pull on the films and risk fracturing the cellulose nanocrystals before we get to tensile test them. Then we do PDMS, which is our soft substrate. We'll put a mask on top of that, and then we'll treat it with oxygen plasma. What that's going to do is oxidize the surface of the PDMS so that it makes water want to spread out and we can more easily cast CNC thin films. Then, since we put the mask on, it's only oxidized in certain areas, and we can localize our films to a certain part. Then we're going to put on a frame, and this basically, it's a plastic frame, it just makes it easier to handle. If we rotate this last drawing so that it faces you, we can cut out different tensile samples at 0 degrees, 45 degrees, and 90 degrees, and put them in the tensile tester. And that's exactly what we're going to see. So we're using the same experimental setup where we have a tensile tester over a microscope so that we can see fracture. Here's an example of this. We have our tensile tester, and we have our grips with our sample in it. We're going to zoom in, and we get to more closely see the microscope and the sample just above it. How we measure order is via birefringence. So we take two perpendicular polarizers. No light's going to want to come through. Something cool about CNC thin films is that they polarize light. So if we orient the CNC thin film parallel to either one of these polarizers, no light's going to want to come through. However, if we rotate it 45 degrees, a small chunk of that original light is going to make it all the way through the final polarizer. What we can do then is we can plug the intensity in from the 45-degree sample and the 0 and 90-degree samples, and we can use that to calculate Hermann's order parameter, or S, where 1 represents a very well-aligned film. So we have an example of this. We take a line scan along a crack. This is at 90 degrees, so no light coming through. And then we rotate the sample, do the same thing, same scan. We get an intensity that is much higher. And then we back calculate a Hermann's order parameter of 0.42. There are two ways that we can calculate the modulus. First is rule of mixtures. This one's been known about for a while. Basically, it states that each portion of a composite contributes its own properties proportionally to its volume fraction. So since the cellulose nanocrystal thin films are very small, they're not going to contribute a whole ton to the overall modulus and fracture strength of the composite. Second way we calculate it is wavelength of wrinkles. So when we pull on a film, since we're using PDMS, which is a soft substrate, it's going to generate a compressive stress in the opposite direction. That's going to make the PDMS want to wrinkle. By analyzing the wavelength of these wrinkles, we can calculate the modulus of the CNC thin film. And here we have our first results. So I'm going to play a video for you here. This is a film oriented at 45 degrees. I want you to keep your eyes on this part right here. You'll start to see first fracture. Yeah, there it is. And then you'll see the rest of the film go directly after that. What's cool about this is that first fracture, you can see where it occurs because the modulus of the overall composite is decreasing. As soon as that cellulose nanocrystal film fractures, it's no longer contributing its properties to the overall composite, and you can see a decrease in stress versus strain. So walking through the images of these films, this is 0 seconds before we start pulling on it. This portion is right here. And we'll get to first fracture, and you can see this is how we calculate fracture stress, is when this graph changes slope drastically. And so the modulus that we calculated from both rule of mixtures and from wrinkles were both 0.4 gigapascals. They agreed with one another quite well. Now we have some more results. The camera works kind of shaky on this one. That's my bad. But you can see first fracture up here as well. And again, we'll step you through this. We have our fracture stress, wherein the material fractures. Right there, there's our first fracture crack. And we have the film, which is completely broken. And we think the results from this one are off a little bit because the film was pre-wrinkled before we actually tensile tested it. So we came up with a rule of mixtures modulus of 2 gigapascals and a wrinkling modulus of 0.1 megapascals. Step through the last one. This one's oriented at 90 degrees. So this is, we're pulling on those weaker hydrogen bonds here. We should see cracks starting to propagate vertically. Yeah, there's a big one. And so again, if we walk you through these images, we have our first fracture, and then we have, after the film is completely broken down, we can calculate our fracture stress from that, and from wrinkles, and we get moduli of 0.24 gigapascals and 0.11 gigapascals. So our conclusions, we have all of our stress strain curves here. The fracture was well correlated to what we found in the angles. We saw some accurate results as far as seeing each of the different fracture modes occur. What we didn't expect, however, is this increasing trend in fracture stress, actually. So as alignment angle increases, we expected that the fracture stress would decrease with the modulus. So what we think that's due to is pre-cracking in the films, and that will bring us to our path forward. Most of the films that we have tested have been pre-cracked, and so these were cast with a miter bar, basically a bunch of wire wrapped around a bar, and we roll the CNC films on to apply shear and to align them. What we think this is doing is cracking the films. Now, what we've been switching to recently is called flow coating, which provides much less cracking in the films, and we hope that'll get us some more accurate results. Next, we want to reproduce this curve, basically. We want to take a bunch of different subdivisions of the angles aside from 0, 45, and 90, and we want to test them all out. So for acknowledgements, I would like to thank the National Science Foundation for funding on this, and also the members of Chelsea Davis's research group. You guys are awesome. Thank you for all the advice, all the jokes, all the stuff in lab. And with that, I will open it up to questions / end this presentation. Thank you so much for joining me. It's been my pleasure. Once again, my name is Dawson Smith, and this has been observing fracture and mechanics of CNC thin films.